today we're going to be doing problem 1.14 and 1.15 of the textbook. So let's start 1.14. 1.14 says find x of 1 of f convolved with x2 of f for the spectra shown in figure P1.1. Alright, so I'm going to go ahead and draw x1 of x and x2 of s. So if this is given to us, so given x1 of f, so x1 of f is 2x. Let's see here, right there. This is at minus f naught. This is at f naught. And this is 0 here. This is the x-axis, or this is the f-axis rather. And then the amplitude is 1. And then x2 of f, same deal. We have two deltas. So we have a delta here, center is at minus f naught, and it says some value, some amplitude called k. And we have a positive one also at k, at positive f0. And so what they want us to compute, they say compute convolution. So x1 of f convolved with x2 of f. Right? So what we'll use here is a couple properties. Number one, we're convolving something. So when you convolve something with a delta, so when you convolve, so you say f of t convolved with delta of t, right? It just becomes delta of t, the function center at the delta, right? So the function gets shifted over to the delta, which is cool, no problem. So here what we have a function that's already shifted and then convolve the delta that's shifted. So let's go ahead and compute. Let's first we have f of t, right? So our f of t here actually is our f of t is x1 of f. So x1 of f here, let's go ahead and write the equation for that. So it's 2 tries. So 2 tries, so it's going to be try. We don't know what the distance here is. So it'll just be try of f. The amplitude is 1. And let's just say divided by some value, let's just call it a, where a is this distance here in the triangle, right? Let's not use a here, actually. A is already being used. Let's just use cap T, right? So we have 1, and actually this would be if the try was centered at 0, but here the try is shifted to minus f naught, so we're going to add whenever you go to the left, you add here. So it's going to be add, and this is the distance from the middle of the triangle to the end of the triangle. And we have plus try of f, because we're in the frequency domain, right? And then this is going to be minus, or this is this triangle here. When you go to the right, you subtract. So this is our function x1 of f. x2 of f is going to be equal to, so we have two deltas with a height of amplitude of k. See here it was an amplitude of 1, so I didn't put 1 here, but this would be 1 times try. 1 times try here, but here it's k, so delta of f plus f naught. So this would be, because when we go to the left, you add. So this is going to be the delta on the left, to the left of the axis, and then over here we have plus k times delta f minus f naught. Cool. And so a note here to make when we're computing this convolution is that convolution is distributive over addition, which would also make it distributive over subtraction as well. But the reason this is important, we can basically convolve these two with this delta, then convolve these two with this delta, and then combine them all together at the end. So I'm going to convolve these 2 tries with the first delta, and then convolve these 2 tries with the next delta, and then compute it all at the end. Or we can just distribute it all right now, but I'm going to do it in steps. I'm going to do the first delta, then the second delta. So first delta here, we're going to get try of f plus f0 divided by t convolved with delta, so k, write this a little clearer, k delta of f plus f naught. So this is my first delta, by the way. This is the first one. This will be the second one. So convolving these two, and then like we're gonna use the property distribution. So we convolve this one with the delta, and then convolve the second trie with the delta. So trie of f minus f naught t convolved with, so use the convolution symbol here to make it really clear. Convolved with delta f plus f naught. All right, so now we're going to compute this. So to compute this, we're going to use this idea up here, which means that when you convolve something with a delta, it just shifts the function to the center where the delta is centered at. And so here the delta is centered at f naught, so this is going to shift it f naught over. And so it's actually centered at minus f naught, so we're going to go over minus f naught. So here we're going to get f of minus f naught. So it's going to be f. It's going to be plus f naught plus f naught. So this is in parentheses. C. And then over here we're going to have plus trie of f plus f naught, right, minus f naught divided by t. All right, so what you notice here is this one shifts all the way to trie of f plus 2f naught divided by t, and then over here we're going to get a plus trie of f. So these are going to cancel because this is f plus f naught minus f naught. F naught's canceled. So now we have a trie here. Oh, we also forgot the k's as well. Let's not forget the k's. K's are the amplitude. So both of these are going to have an amplitude of k. So let's put that as well. This is going to be k. This is going to be k here. Where k is the amplitude of the deltas. And so k is just a multiplier. So a convolution really is just an integral with the time shift. And so when you integrate these two together, you can always factor the k out because it's just an amplifier. So it'll be factored in at the end. So these will be multiplied by k here. So what we end up with is a trie. Now we have a trie centered at 2f naught because it was originally, remember the trie was at minus f naught, and then with the delta being at minus f naught, it shifted it over one more f naught. And so then this one was at positive f naught, and it got shifted over in f naught. So it went f naught all the way back to 0. And so now let's compute the second one. So let's compute the second delta. And we'll put the results here, right here on the same line. Okay, so that was the first delta. Just erase that so we have a little more space. The second delta. Okay. It's going to be, so these two convolve with this guy. So it's going to be trie of f plus f naught divided by t, where t is the duration of the half the triangle. We don't know. I'll put that out there again. Convolve with k delta f minus f naught. Alrighty, and then plus trie of f minus f naught over t convolved with k delta. So convolved with k delta f minus f naught. So what we're going to do is we're going to end up with trie. And so here we have minus f naught. So this is going to be f minus f naught plus f naught divided by t. And they're going to have plus trie f minus f naught minus f naught. This is going to be inside divided by t. And so we end up with, this is going to be k. This is going to, I keep forgetting my k's, guys. There are k's here. Multiplied by k. This is just an amplifier. So this is going to end up being k times trie of, so we have f minus f naught plus f naught. So minus f naught plus f naught cancel one another. So you end up with just f over t. And then over here we're going to get plus k trie minus f naught. That's minus 2f naught. So then you get a triangle shifted over 2f naught. Just how you have one shifted over to the left 2f naught, you get one shifted over to the right 2f naught. And so this one ends up being f minus 2f naught divided by t. And then you can add, basically you add these two together. So the only thing that's really interesting here when you add them together is you have two triangles centered at, you have two triangles centered at f equals 0. You have two triangles centered at f equals 0, right? It's this one and this one, right? They both have an amplitude of k. So this is going to shift it up because they're basically how the graph is going to look is, right? The graph is going to be like this. We'll graph it to show you all. So remember we have. So let's start with this one. So we have a triangle here with amplitude of k. This is k, and it's centered at f equals 0 because there's no shift here on the f. And then we have one at minus 2 f naught. So with the amplitude of k, this is minus 2 f naught. And then over here we have another one at positive 2 f naught. And then finally we have this one again, so we have another one here, which I'll draw in a black maybe. Right, we have another black one, and so these two are going to add constructively to one another. So 0, 0, and 1, 1, and then, so at the end this is going to end up being 2k, right? So this one's going to, when you add these black and red one together, since they're at the same place, this one's going to end up being 2k. Because it's two triangles added to one another. And so in the end, you end up getting 2k. Because at the highest of the amplitudes is k. And so when you got it, it's going to be 2k. And the triangle is going to be steeper, of course, because the amplitudes is rising at a quicker rate because they're being added together. And so here you end up with 2k. So you end up with a triangle that has 2k. And then at the origin, and you end up with two triangles at minus 2 f naught and positive 2 f naught with height of k. And if you want to rewrite this, basically what you can do is the equivalent formula, because it says compute, so we can do a graph net, or we can compute it using an equation. But the equation would be k tri of f plus 2 f naught divided by t plus 2k tri f divided by t, and then finally the last triangle plus 2k f minus 2 f naught divided by t, where t is just an arbitrary value I chose for half the rectangle duration. Right. So this will be your final equation, and this is the graph to represent it. So this question's not too bad. You just have to know that when you cross with a delta, it just shifts the function over to the center of that delta. If the function itself is already centered, then it's going to shift it over more past beyond where the delta is centered. So that's why here we got minus 2 f naught, because the function was already centered at f naught. And so you got to shift f naught, and you got to shift f naught beyond where the function itself was centered at. And so that you have to take into account that, of course. So this is that problem. Let's go ahead and move on to the next problem, which is problem number, I believe, problem number 1.14 and 1.15. So let's get into that one. All right, problem 1.15 says the two-sided power spectral density function gx of f is equal to 10 to the minus 6 f of f squared of a waveform x of t, which is shown in figure P1.2. Find the normalized average power in x of t over the frequency band from 0 to 10 kilohertz. Find the normalized average power contained in the frequency band from 5 to 6 kilohertz. All right, so they basically computed the average. The integral. Let's go back here. And first, let's write our givens. So our given, we have gx of f. It's a function. It's 10 to the minus 6 f squared. It's a quadratic, right? Because we have a squared term here, a second degree term. And so we know this is our power spectral density function. We also know that a little, if we go back a little in the chapter, we know that the average Norris power can be computed by the integral from minus infinity to infinity of gx of f, which is what's given to us, right? df. This is not a delta, guys. That's a d. All right, now it's a d. Look like a delta before. So this is the average normalized power. We know that this is the case, and so if we want to compute it over a range, we just change our bounds. This will give us the total normal normal average power for the whole signal. This is, if we choose the range, it will give us the total normalized average power for a certain range. And so what it asks us to do is says find Px of f for 0 to 10 kilohertz, I believe, and then find Px of f for 5 to 6 kilohertz. So that's not too bad. What we're going to do here is we're just going to integrate this function over these two bounds and compute it. So for A, we're going to do from 0 to 10. Let's do kilohertz here. Kilohertz is time 10 to the third. So this is going to be 10 to the minus 6 f squared. I'm going to factor out this 10 to the minus 6. It's going to be df. We 10 to the minus 6 of 0 to 10 thirds of f squared. Well, that's going to be f to the third over 3 times 10 to the minus 6 for 10 thirds to 0. And so what you end up with is 10 to the 3 times 3 is 9th times 10 to the minus 6 divided by 3. Well, that's going to be, we're going to add these together, you're going to get 10 to the third divided by 3, which is 1,000 divided by 3, which is approximately like 333.33, I believe, repeating. So that's the average normalized power. And then B, 5 to 6 kilohertz, we're going to do the same thing here. So I'm going to skip down some steps. I'm just going to go straight to 10 to the minus 6 from 5 to 6. F squared df is going to be 10 to the minus 6 f third over 3 from 6 times 10 to the third. 5 times 10 to the third. Oh wait, did I do? Oh, 10 kilohertz. All right, we gotta go back, guys. This should be 10 times 10 to the third. I'm sorry. That's because 10 to the third is 1,000, and that's gonna be 10 thousandths. So this needs to be 10 times 10 to the 10 third, which is different. This answer right here is wrong. Up here you should end up getting 10 times 10 to the third to the third power times 10 to the minus 6 divided by 3. You can compute that. That's not that crazy. You can put this in a calculator. That'll give you the answer for this question. And then the same thing here. You're going to end up with 10 to the minus 6. And then you're going to get 6 times 10 to the third power divided by 3 minus 5 times 10 to the third power divided by 3, and then times 10 to the minus 6. And you put this in a calculator and it'll give you your answer for your average normalized power for these two. So this question is pretty straightforward, pretty simple. That's going to be all today, guys. Hope you enjoyed.